Hello all, let us talk about boost regulator in this video. In the previous video, we have talked about the buck regulator, its basic principle of operation, and we have simulated in LT Spice. In this video, we will talk about a boost regulator. Boost regulator, if you see a simple circuit, this is the basic circuit of a boost regulator where you have a inductor and then switch, a diode which has a low forward voltage drop, and then capacitor and then the load. This is the simplest circuit. So this almost looks similar to the buck regulator, right? But the major difference is that these three components are interchanged in their positions to achieve a higher voltage than the input voltage. So what does a boost to do? Boost just gives a voltage, output voltage greater than input voltage, right? So these three components play a major role in performing that operation. So let us see how this happens. So, first condition, when the switch is in on condition, that means this particular switch is in on condition. So, what happens is the current flows through this loop, okay, and during this time, the inductor gets charged. So, the voltage across the inductor basically increases due to the current flowing through it. So, in this case, this diode is in off condition and the capacitor actually provides the supply to the load, or basically it provides the required load current. Now in a state where the switch is in off condition, okay, so the input is connected through the inductor and diode to the load. So in this case, what happens is the the input voltage Vi, okay, gets added up to the inductor voltage VL or whatever you take, and in the process, this particular diode is forward biased, and you see that the capacitor as well as the input voltage providing supply to the load, and at the same time the capacitor also charges up uh, as in the switch on condition. That means in the previous cycle the capacitor has provided enough current, so now the capacitor um, charges, and also the output V naught is provided such that it is basically Vi plus the VL. So if you see this loop, this is how it works. So minus voltage drop that is there. So we select a Schottky such that we have lowest drop as possible. So that's how a simple boost regulator works. So here the major things that we need to keep in mind is how the inductor develops voltage and what is the potential that is developed around the inductor and how the capacitor provides load current, and when the diode turns on, that's it. And especially at what frequency you are switching the um, switch that is present in this topology. Now how does a current flow? So as seen in buck regulator, the current through the inductor is crucial, and the average current that is flowing through the inductor is the actual load current, which uh, each can be provided by this regulator. So now in buck regulator we have seen that the current on the inductor is a ripple current where uh, during the on cycle the inductor current increases through the inductor, and during the off cycle the current reduces. Similar scenario here, where when the switch is in on state, that means the inductor develops more voltage. Okay, the current through the inductor increases, and so through what condition we know, right? VL is equal to L into di by dt. Okay, so this is the condition. So the rate of change of current into inductance, okay, of that particular inductor gives the voltage developed. So this is the change in current which enables voltage being developed across the inductor. So the on and off condition determines how much you are turning on and how much you are turning off, determines the output voltage. So this is how a simple boost regulator works, right? Almost, if you know about a buck regulator, being a beginner, you know how a boost regulator works, with just components being interchanged here and there. Now let us see the simulation of the boost regulator. Here is a simple circuit of a boost regulator, where we can see here we have a 12 volts, okay, and then we have inductor, okay, uh, which is in series with the supply, and then we have a diode. So diode is selected such a way that you have low series resistance for the diode, and we have a low forward drop. That's the criteria for selecting the diode. So select your diode, and especially the availability. So based on that, you select your diode, and then the capacitor must be able to hold the charge and provide the load load current during the switch on condition. So that's how we select these particular components. And inductor again plays a very crucial role, because the rate of change of current through the inductor develops the voltage, and this voltage is what adds on to the supply. So inductor selection is very crucial to achieve the desired output. Now here, if we just see the output, okay, output is given by V in divided by 1 minus duty cycle. So this is the formula for the output voltage. Now if you see here, we have a PWM signal which is driving the switch here. Switch is a MOSFET. Again, the MOSFET is an N-channel MOSFET. So select a MOSFET which has sufficient VDS and sufficient current. So the current through the MOSFET must be such that it matches with the output load requirements. Okay, so select the MOSFET in such a way, and what we are doing here is we are selecting a 50% duty cycle. So if so the time period here is 10 microfarad, that means we have taken a 100 kilohertz signal with 50 kilohertz on time and 50 kilohertz off time. So the duty cycle is zero point 0.5. So if we put 0.5 here, 1 minus 0.5 is 0.5, which means V in into 2. So that means the output voltage must be twice the input voltage. So that's how the output is determined here. So let's try to run the simulation. Okay, when we try to run the simulation, first thing, let us see how the input voltage is, and the next thing, definitely the output voltage. So you can see here it's taking some time. This sharp rise in voltage is due to the inductor. So and within a short time, the voltage almost settles to 24 volts, right? So as we have seen here, this is how the output is. So definitely the output drop will not be exactly as per this formula, because there is a diode drop here, right? And then one important point that we have talked is the ripple current on the inductor. So as we see here in this waveform, let us try to delete V03, okay, and let us try to expand this. You can see the ripple current varying between almost zero point 0.2 to zero point 0.8. Okay, so that's how the current is. And then if you see the load current, okay, so IR1, it's almost 250 milliamps. So this is the load current. And then we need to know the PWM waveform, right? So PWM waveform, as we have mentioned, is a waveform which helps to switch on the load. So if you see here, this is 12 volts. So the rise time is kept very low, and the cycle is such that T on is 5 microseconds and T off is 10 microseconds. So that's how the waveform we are getting here. And then let us try to delete all this. Let us try to delete. So let us try to concentrate on the output voltage. So you can see here the output voltage is increased, right? It is 24 volts from a 12 volts input. So that means the voltage got boosted here. So this is how a very basic boost regulator works. Now, there are many principles involved here. One is how the inductor voltage gets developed, what is the principle of operation of the inductor, how to select a capacitor, okay, and then basic selection of PWM, the switching frequency, and all these parameters we will discuss in another video, but this should give a very high view of how a boost regulator works. Please post if you have any questions. Thank you.